we're going to have a look at this one. This one has obviously a vector component to it. Okay, it's going to change directions because what goes up must come down. Okay, so we know then that there's a change in direction. So I'm just going to quickly make a note that positive will be up and negative will be down. Okay, that way when I'm writing out my givens, I know which ones should be negative and positive. All right, so an object is thrown up in the air at an unknown velocity. Well, that's where the question starts. So I'm not going to write 0. I'm going to write, I don't know. I don't know what VI is. Okay, it says it's unknown. All right, it's in the air for 6.5 seconds. What did they just tell me there? Okay. Okay, its final velocity is 2.4 meters per second down. What did they give me there? Yeah, good, because they just said it was actually the final velocity, so good, everybody's awake. Okay, negative 2.4 meters per second, and obviously acceleration due to gravity, which is something we talked about yesterday, is negative 9.81 meters per second squared, because it's also down. Okay, with me so far? So I'm trying to find VI, which is the trickiest manipulation of the acceleration formula. All right, so we get a mark for writing that down. Then we got to multiply both sides by t. Then we're going to add VI to both sides. And then we're going to subtract t times a over to this side. So we'll be left with this. VI equals VF minus t times a. Okay, so VF, we were told, was negative 2.4 meters per second minus 6.5 seconds times negative 9.81. It is crucial that we get the positives and negatives in there. All right? If I don't, then this is going to tell me that I made this thing go the way it did by throwing it down. Okay? Obviously, I didn't throw it down. The question says I threw it up, and not I mean like vomited. I mean I actually threw it in the air. Okay, so we have negative 2.4. Okay, minus whatever negative 6.5 times negative 9.81 is. All right, so come on. Negative 2.4 minus 6.5 times negative 9.81. All right, so it was thrown up in the air at 61.4 meters per second. Which is really fast. I don't know anyone who throws anything that fast. Okay, that's like nearly 200 kilometers an hour. Right? So 61.4 meters per second. What needs to go here? Up. Okay, are these starting to make some sense? All right. Yesterday, Alec was telling me about this thing that NASA launched, the DART mission. So I was reading about it last night because I'm a nerd. Okay. So this thing actually has a lot of applications for what we're doing right now. So this thing that NASA launched yesterday, NASA and SpaceX launched it yesterday, is basically just a small probe, and all it's going to do is get going really, really, really fast, and then it's going to smash into an asteroid. Okay? The hope is that they'll be able to change the velocity of the asteroid by even a tiny little bit. Right? So what they're doing, and this has to do with some of the energy stuff we were talking about as well, okay? They've got one asteroid that's big and one asteroid that they call its moonlet that's smaller, okay? And the smaller one orbits the big one, right? And they're just moving around the sun. They're no danger to Earth whatsoever. What they want to do, since they know how long it takes the little asteroid to orbit the big one, is they're going to smash this thing into the little one, right? And all that's going to do is slow it down just a little bit. And when it happens, it'll be close enough to Earth that they can see it through Earth-based telescopes and actually observe if now it takes a little longer for it to orbit the asteroid. If that's true, then they get some idea of whether or not they have any hope of redirecting an Earth-killing asteroid. Okay, so all this is like a proof of concept, kind of, okay, for whether or not we could defend ourselves from an incoming asteroid that could smash into the Earth. Okay, so how much do you suppose they're going to be able to change the speed of this asteroid by?
Not a lot.
Not a lot. Okay, they're hoping, I think they said, for changing the period of its orbit by a few seconds. Okay, so not very much at all. But it's still changing the velocity, which is that it's causing a what? Change in velocity is that thing we were just working on? Acceleration, right, okay? A change in velocity is acceleration. In order to accelerate something or change something's velocity, we have to do work. So what they're hoping for is that they can get this thing going really, really fast so it has a lot of what kind of energy? What kind of energy do you have because of your movement? Kinetic, mechanical as well. Okay, so this is their thing, the Double Asteroid Impact Redirection Test, or DART. Okay, so this is the spacecraft that they're going to use, and it's got this big engine on the back that's going to be used to crash it. Okay, so this is like high-tech science. Smash it into something. So they're going to have that going. Okay, what do they say? So the big asteroid is 780 meters across, and the little one that they're going to smash into is 160, which is more typical for asteroids that could pose a significant threat to Earth, because the bigger they get, okay, the less likely they are to have their orbit change and then be a worry for Earth. Okay, so this is kind of what it looks like right now because it's a long way away. Okay, that's the big one and that's the little one. Okay, and so really all they're hoping to do is make this thing go really fast. Okay, so it's going to crash into the moonlet at 6.6 kilometers per second, which is pretty fast. Okay, and then it's just going to hopefully, so they're hoping it'll change the orbital period by several minutes. Sorry, not several seconds. Okay, several minutes, enough to be observed and measured by telescopes on Earth. So that's kind of how that's going to work. But we're talking about having to do a fair amount of work that is transferring mechanical energy to this moonlet, right? Now, they're not trying to make the moonlet go faster. Obviously, they're trying to make it go slower or knock it further away so that it takes longer to orbit. They weren't really specific on how that was going to work. Okay, one or the other will make the orbit take longer. Either they're going to make it go further away from the asteroid and take longer to go around, or they're going to slow it down. Okay, all right. So yeah, that's kind of the idea there. Okay, so the spacecraft will just run into the smaller one and hopefully redirect it. Now, what that'll tell us is how much mass and how much velocity we need in order to change the path of an incoming asteroid. Right? If we do it early enough, we don't need as much because we can change its course when it's a long way away and give it years to move out of the path of Earth. If we wait till the last minute, then we have to have way more mass and way more velocity because we have to change its course quickly. Okay? We want to be able to use like a small amount of acceleration to change the velocity by a little bit, okay, just to make it go away, as opposed to, oh crap, here it is, we better swerve. Okay, kind of a thing. So it's still kind of what we've been talking about. It's work and energy. It's causing a change in velocity, but it's something that's applicable at least. So this is one of the places you'd use what we're learning. Okay, the other thing I want to see if we still remember, because we didn't actually finish this one the other day, was this question here. Okay, we did the accelerations. Okay, of the two parts, so we did like A and D, but we didn't do the total displacement over the whole trip or the average velocity over the whole trip. So, on a velocity versus time graph, if I want to calculate the overall displacement, what do I have to do? Anybody remember? Something to do with shapes. Area, right. I got to find the area between the line and the x-axis. Now, when it's just a single line like this, it's a lot less work. It's like a triangle and a rectangle and we're done. Okay? On a graph like this, well, there's a few more shapes to calculate the area of. Okay? So we need some right angle triangles and some rectangles and things like that. So, okay, is there any displacement right here between 0 and 2 seconds? No. Okay, but there is some displacement here between 2 and 5 seconds where the object is accelerating negatively. And then there's some displacement right here where it's accelerating positively. All right, so those are two separate triangles because obviously it's not equilateral. All right, and then there'd be some more displacement right here where it's accelerating. And then, what's going on in this part right here? It's doing what? It's moving at a constant velocity, so there's still going to be some displacement there. There's going to be a little bit of displacement here for this half a second, okay? And then there'll also be some displacement in this triangle here, which would be 1.5 seconds on the base. Okay? Then we'd have like a triangle here, and this rectangle right here, and then that triangle there, right? That we would have to do all the area calculations for. Okay. I'm going to let you guys calculate those areas and see if you get the answer that they've got here. Negative 12 meters. All right? All right, we'll give you a few minutes on that one. Would I give you one like that on a test that had that many shapes? No. Okay? I would give you one like this that has like 2 shapes. Okay? That would be easier. It still tells me I know how to do this, but it doesn't mean you have to do it 8, 9 times. And you'll have to do it twice. All right, give that one a try. I'll give you a few minutes on that one. Okay, let's have a look at this. So we just have to find the area of all these shapes. Okay, we can recognize obviously what's going on in each part of the graph, accelerations, what direction they're going, constant velocities, what direction they're going. Okay, but to calculate the actual displacement, we need to take average velocity times time, which as we've said many times is calculating the area under the line. Okay, so for this first triangle here, we have a base of 3 and a height of -3. So 3 times -3 is -9, but it's a triangle, so divide by 2, we got -4.5 meters there. Okay, then we've got this little triangle here, height of -3, base of 1. Okay, so the height, so that would be -3 divided by 2. This will be -1.5. Then we've got this triangle here that is a height of +2 and a base of 1. 2 times 1 is 2, divided by 2 is 1. Okay. Then we've got this rectangle that has a base of 1, 2, 3, 4, 5, and a height of 2. 2 times 5 is 10. Okay. So 10 meters, 1 meter. Okay. So this is positive. This is positive. Then we've got this little one here, okay, that only has a base of 1/2. Okay, 1/2 times 2 is 1, divided by 2 is 0.5. Okay, then we've got this really tall triangle that has a height of -6 and a base of 1.5, so that's -9 divided by 2 is -4.5. Okay, then we've got this triangle here that has a height of -4. Okay, because it goes from -2 to -6, and a base of 2, so that's -8 divided by 2, -4 meters. We've got this rectangle that has a base of 1, 2, 3, 4, and a height of -2, so that's -8 meters. And then we've got this last little triangle, base of 1, height of -2, okay, divided by 2 is -1 meter. All right, so just basic geometry to calculate all those numbers. Now what do I have to do with those numbers?
Add them together.
Right, put them all together, okay? Keeping the negatives and positives in mind because they want displacement, which is a vector quantity. All right, so we got -4.5, -6, okay, and then, you know what, I'm just going to talk rather than try and keep track of it in my head. Okay, let's go here. So, -4.5 plus -1.5 plus 1 plus 10 plus 0.5 plus -4.5 plus -4 plus -8 plus -1. All right, -12. All right, so the total displacement is -12 meters, which, if we look at the graph, makes sense. On this graph, the object spent way more time in the negatives than it did in the positives, right? So it makes sense that its overall displacement should be negative, right? And it was accelerating and traveling at a constant velocity and accelerating and traveling at a constant velocity all over the place, okay? But in the end, it ended up behind where it started. All right, I'm not going to give you one like that on a test because it takes too long. Okay? You can show me whether you remember that it's the area under the line with a much shorter question, and that's what I would do on a test. All right. Did we talk about this one the other day? I know I went over it with one of my classes. Must have been period 4.
I'm just wondering, so before, when we just did, like, you had to find the rectangle and then the triangle on top, if the line started at 0, you just try to find the area of the triangle?
Yeah. Yeah, because there wouldn't be a rectangle under it.
Okay.
Okay, so another velocity versus time graph. When people look at this, they often don't realize what they're seeing. Okay, and this is really the importance of analyzing a graph. When I give this question, I used to give it on a test. Okay, this was a question that I thought was going to save people time on the test, and it ended up doing the exact opposite, because people ended up actually doing a whole bunch of calculating that they didn't need to do, right? Because they didn't look at the graph and interpret what's happening. So let's do that first. Okay, so on this graph, right, for part of the time, in fact, exactly half of the time, the object is traveling. What's that?
No.
Forwards or backwards?
Forwards.
Okay, forwards. This would be the forward part up here. And for this part, it's traveling backwards, right? Because its velocity is negative for the first 10 seconds, and then it's positive for the last 10 seconds. What do you notice about the two halves of that graph? Yeah, but equal but opposite. Okay, now if you realize that, how long does it take you to figure out what the displacement of this object would be? Very little time. If it does exactly the same thing backwards as it does forwards, what's its total displacement?
0.
Right? Didn't have to do any calculating. Just had to look at the graph and recognize that. Okay? Does everyone kind of follow me there? Sometimes you get a question that's actually that easy. Okay? Like this should really just be a multiple choice question because it doesn't require any calculation. People might actually calculate on it, but I think that's a waste of time. If I can interpret this graph, I can see, and even if I go as far as to go, all right, I'm going to draw the shapes. Okay, so, oh, wait a minute. These shapes are exactly the same. No, okay, then I'm done. Actually, I didn't draw that one in the right place, but okay, should be 1 second over here. Okay, I can look at that and go, oh, it did exactly the same thing forwards and backwards. I don't need to calculate the areas of those shapes. I know they offset each other, and I'm done with that question. All right? Making sense? So we'll probably spend a couple more days on acceleration and velocity versus time graphs next week. I have a lab plan, okay, for next week as well, velocity versus time. But reminder that your plant projects are due on Monday, okay, and your position versus time graphs Tuesday. Okay, so make sure you get those two things done over the weekend, okay, if they're not already done. And if you want me to look over your position versus time graph labs, obviously you can bring those in on Monday, okay? But I won't be able to look over your plant species projects now. It would be too late. Okay. Last thing before we start packing up here. I want you guys to calculate the average acceleration over the whole trip from this graph. Okay, remember that's your acceleration formula. Incidentally, guys, if you have lost your periodic table, get a new one, okay, or print a new one from home, because the formulas are on the back of it, and the formulas are going to start to pile up here. And you're going to need to be able to refer to your formula sheet, because I don't want you to memorize them. Okay, so if we're quickly looking at this, this is just a very simple acceleration problem, okay? Much easier than the ones we started class with. So our final velocity, positive 8. Our initial velocity, negative 8 over 20 seconds. So we've got 16 over 20, so that should be 0.8 meters per second squared. Okay. All right, we'll leave it there. If you guys can clean off your desks, I gotta come around and spray them off.